we kind of talked about the idea of GLS. So if you remember, there's this setup that you are working with. So the covariance of epsilon or the noise in regression being sigma squared I. And then we argued or showed that the OLS estimator is the best linear unbiased estimator in this case. And then the question is that what happens if this condition fails? Let's say the covariance of matrix of the noise is sigma squared V for some known V. And the idea is that OLS is not going to be, it's going to be unbiased though, but it's not going to be best in the sense that it doesn't minimize the variance. So the good news was that we could fix this really easily. If we know V, we do a sort of whitening procedure. Whitening means restoring this covariance matrix, basically, the structure. So what we did is do a Koleski decomposition, and then you do a transformation like this, L-1 applied everywhere. And then you get these transformed variables, and then easily you can show that the covariance of this transformed noise is sigma squared I. So in this transform model, we can do OLS, and it would be best linear unbiased estimator, and that fact doesn't kind of interfere with the fact that we did the transformation. It's a statistical procedure. You can't like improve. It's like the statistic. You can't change the statistical properties by just like transforming the data. So if it's best in this model, it's going to be best in the other model as well. So this is going to be best linear unbiased estimator in this transform model. So when you transform back, it tells you that this guy is the best linear unbiased estimator. And we really didn't talk in general about this being also a solution optimization problem, but let me just briefly mention it in the WLS. But this is really minimizing y minus x beta in a new norm. So a norm I would call V. So norm squared in this V inverse norm. So if you minimize this, this is really the solution of this least squares problem. It's not ordinary least squares, but least squares in a like a different norm. The norm here being, do I have it here? Yes. So if you look at this slide, just briefly mentions. So if you look at a quantity like this, A transpose V inverse B, this you can think of it as a new inner product. There are some general rules in mathematics to define inner products, like abstract bunch of axioms, and this satisfies the axiom. It's like a bilinear positive definite form or positive form, like faithful in a sense. I mean, there are a bunch of if V is invertible, this is going to define a valid inner product, and it defines a norm in particular. Why like the norm of A would be this. Sorry, A inner product of A with itself. When you have an inner product, you have a notion of norm, and you have a notion of length. We discussed this. So this is really going to be A transpose V inverse A. So in this sense, we are minimizing kind of y minus x beta in this norm square. So you can call this the V inverse norm or whatever you want to call it. So it's really solving a different least squares problem. It's just you can show it is equivalent. So this formula that comes out is equivalent to solving that problem. And in particular, in the weighted least squares case, because this V inverse is kind of diagonal, we saw that this is diagonal. Like it's equivalent, like the weighted least square is equivalent to the GLS case where V is diagonal. And then this optimization problem becomes like a weighted least squares. So this business is going to be equivalent to basically this. the cost function is going to be a weighted average of these deviation squares. And then it was kind of, we discussed this, that this makes a lot of sense from a interpretation perspective, because these weights are basically proportional to the inverse of these variances, so sigma I squared. So whenever sigma I squared is very large, Wi would be small, so if this downweights that particular sample. Whenever sigma I squared is small, it means that you're have more confidence on that sample, so this would upweight the sample. So it's a very natural way to define an estimator. So you minimize the errors, but you weight them differently depending on how your prior belief about the noise, right? So if you know that this sample has low noise, so you want to try to do a better fit there. If you know it has a high value of a noise, you don't want to do you don't want to fit that well to that particular data point. Okay, so it has a lot of intuition built into it. And so the fact that this turns out to be kind of optimal thing to do is no surprise. Does this kind of interpret? Did we talk about this? It's very good to try to go through and understand this. It's like a very natural way to interpret. And then the general case is this. It's not going to be diagonal, but it takes into account all the variation in different directions. We're going to talk about a little bit about this idea that variance has directions today. But anyway, so the thing that I wanted to maybe expand a little bit on in this idea of feasible GLS. So far we had, or up to this point, the V was known. So you knew the, so we had the covariance of epsilon sigma squared V. We assume we know V, then we can calculate the GLS. And by the way, you can basically translate everything that we did, the estimate of the variance, the confidence intervals, the F test, the T test, everything would just transport back and forth. So if you, in the transform domain, for example, this is how you estimate. This is the residual squared divided by n minus p plus 1 is how you estimate the variance. And so I can replace the tilde version. So y tilde, x tilde, and beta tilde can be written in terms of the original yx and like a v. And so what you get is that, actually beta is, you leave it the same, but y tilde and x tilde, once you plug back in, you would get this formula. So, and then I think you have a homework problem to try to figure out, let's say if I want to do prediction interval, what it would look like. Okay, so it's a very good exercise to try to transport that machinery via this transformation to this domain. So everything that we did is kind of go through. The issue is that in practice, you don't usually know V. You may know some, you may assume some structure. This is a particular case where we have a nice structure. So if you have a time series, for example, model, the data has a time axis, it's very natural to assume that maybe the noise has some serial dependence. So there's this AR1, autoregressive of order 1 process that we can assume, for example, that noise follows, let's say today's value is not independent of the yesterday's value. Okay, so today's value is a scaled multiple of the previous day. Rho plus a quantity which is independent, okay, like a scaled multiple of UT, which let's say UT is an IID sequence, normal 0, sigma squared. Or at least uncorrelated. So, so if rho, for example, here is 0, then epsilon t would be equal to ut. So we get back the original setup. If rho is equal to 1, it's the worst case. So all the coordinates of the noise are the same. But if rho is somewhere, let's say between 0, I mean, 1 is okay included. Sorry, 1 not included. Could be 0, that would be best case. And then maybe all the way up to 1, but not equal to 1. Then we have a nice dependence structure, okay? And then you can calculate the covariance of epsilon s and epsilon t, and you would see that the let's say, you have to worry a little bit about the initialization, how to initialize, let's say, epsilon 0, for example, or maybe epsilon 1 if you want. What is epsilon 1? And then so you can, once you figure out what epsilon 1 is, we can, let's say I define epsilon 0 to be 0, and we don't include it in the sequence, then epsilon 1 really would be, actually that wouldn't work. Let's say epsilon 1 is normal sigma 2, and then this is for t bigger than or equal to 1, something like that. Just maybe double check. Once you have that, you can start the recursion. You can compute these, and for example, covariance of epsilon, let's say t plus 1 and t, one step difference, let's say, would be sigma squared rho. If you go to a step like epsilon t plus 1 and t, you would get sigma squared rho squared. And so as you move in time, the covariance is going to geometrically drop. And so in general, if you're at s and t, like the covariance only depends on the time distance. So we sigma squared rho times s minus c. So this has a Topliss structure. So if you have sigma squared here, you get 1 here, 1, 1, 1, 1, 1 here, and then rho immediately above and below diagonal, and then rho squared immediately above that, and so on. So as you move away from the diagonal, perpendicular to the diagonal, it drops, okay, and it's equal. On these diagonals, it's equal. So this is called a Topliss matrix, okay. Have you seen this structure before? Okay, Topliss matrices they have the same, the structure. And it arises from this kind of serial correlation. If you look at a correlation matrix or covariance matrix of an AR1 process, it has this Topliss structure. So you can see this V is completely determined by rho, but there is still this unknown rho. Okay, so this makes sense practically. I can assume this process, very nice, simple dependent structure, but still I need to estimate rho. And then what you can do is like a very simple idea. You can do different things. You can try to do maximum likelihood or jointly estimate everything. But let's say a very simple idea is that I can fit OLS. OLS still is a relatively nice estimator. I'm going to fit OLS, and I'm going to get these residuals. Okay, so the actual model is we have yt is equal to, let's say, beta 0. What do we have actually? Yeah, let's say we have x beta. I have to write it this way. Let's say xt transpose beta plus epsilon t, and then epsilon t is rho epsilon t minus 1 plus rho squared ut. So the full model is something like that. So I fit this part, and then I get an estimate of beta hat, and then I have the residuals. So OLS, I get beta hat, which gives me E hat. T would be yt minus xt transpose beta hat. And so these are surrogates for the actual errors. Okay, so if I have the actual error sequence, you can see that I can do a simple linear regression. So I can regress epsilon t and epsilon t minus 1. This is the noise part. And I can recover rho by just least squares, solving a least square. Okay. The problem is that I don't have this guy. You fit a simple linear regression with 0 intercept. So regression through the origin, because this doesn't have an intercept. Just has one parameter. So I'm just going to use these residuals in place of epsilon t, and it would give me, if you do the OLS regress, if you do regress et hat on et minus 1 hat, or e hat t minus 1, then through the intercept, so no intercept regression, this is the formula that you get for the least squares estimate. It's very easy to kind of figure out. It's often not the case that your predictors and kind of response are the same thing, but it's like the same sequence but shifted. But still I can like try to do it. So if you look at the response, it's just a shifted version of the predictors, but that's how these kind of models look like. You're trying to predict the future given the past. And so this is a good estimate. And then what I'm going to do is that I know the structure of V. I'm just going to plug in. So I know that VST is just rho to the power, the difference of S and T. And so I'm just going to plug the rho hat. So I get a plug in, and then I use the V hat in the GLS formula. Okay. So if you are pedantic, this should like raise all like alarms because you assume that V is known, and so all the machinery, like the confidence intervals, the distributional kind of results all hold for fixed V. If I replace V with this V hat, it's similar to, for example, replacing sigma squared with S squared. If you remember when we tried to discuss the pivot for the t-test, once you replace things with random quantities that depend on the numerator, for example, the distribution would change from a Gaussian to a t or like to an NF. So in particular, I mean, this would be a lot messier because if you look at for example, you look at the beta hat, or maybe let me look at this, for example, you look at the sigma squared. So this V was fixed, everything would be okay. Now if I put V hat here, this is derived from the same Y, so they're highly dependent, and the dependence is nonlinear. So the distribution of this is not going to be chi-squared anymore. I mean, after, like if you multiply this by that, divided by sigma squared, it's not going to be chi-squared. But I mean, the thing is that in practice, you not necessarily worry. I mean, there are very few cases that you can actually do these calculations. Specifically, the classical t-tests and stuff are an example. In practice, you would be okay with paying the price. So the confidence intervals would not be exact, or the claims that you make are not going to be exact, but asymptotically, they're going to be okay. As n goes to infinity, generally by the law of large numbers, or by consistency of this estimator, this is going to converge to rho. And so this is going to converge to V. So asymptotically, things would become better as n goes to infinity. But for low sample size, just know that things are not going to be exact. But that's the idea of feasible GLS, okay? So you plug in and you call it a day, and you call it feasible GLS, okay? And when there are other, oh, by the way, ways of estimating rho hat, which are there if you're interested. But any questions about this? Does it make sense? So we have a GLS, which in practice we can't implement because we often don't know V. We have a structure for V. And then you try to estimate the parameters. You can estimate the parameters, for example, in this AR one. Setup, the idea is simple. I start with a simple estimator. I get residuals and then regress the residual on itself. I get an estimate of rho, and then I plug in. I get a plug-in estimator for V, and then I use that, and this leads to the feasible GLS idea. Questions? Okay, let's look at a nice plot. So this, I believe I discussed last time. So here we have a simple setup. I think we have like a really simple linear regression going on here, plus that AR1 process, epsilon t is that AR1 process. And so beta 1 is the quantity of interest. We want to estimate beta 1. And you can see here on the left, the confidence intervals for the two methods. So the naive OLS is the red one, and then the feasible GLS is the blue one, and the true beta is this dashed line. And you can see that the naive OLS, the confidence lengths are too optimistic. They're narrower than the feasible GLS, and you can see that they miss a lot more. A lot more of these intervals kind of miss. I don't know if you can see it, but the ones that are bold are missing. So all these things here are missing. These things here are missing. So overall, like 22 out of 42 cases are missing here, whereas the FGLS is like 37 out of 42. Okay, and then this side is basically doing that, like keeps track of the coverage. The empirical coverage is what fraction of these intervals cover, and that should be like around 95% because that's how we set these intervals. The green here is the Oracle GLS. Oracle here is the one that knows rho. Okay, if you know rho, you plug in, you can see it has a perfect so-called calibration. It's calibrated perfectly, which means that it stays at 95% as a vary rho, the AR1 like a parameter. The feasible GLS starts to drop a little bit, but you look at the OLS, it just completely drops to like around 30% at this end. Let's say at 80%, let's say 0.8, rho 0.8 is about 50%. So you calibrate it for 95%, but in practice, it's just covering 50% of the time. So it's too narrow to capture. And so this is a question for you to think about. It could be a question in like an exam, like a final exam. So why the OLS is too optimistic? Okay. And why does it drop? So kind of the fact that it drops is related to the fact that it's too optimistic. Okay. If you want to answer it now, it's possible if you want to think about it. The other thing is that you can see also the FGLS is slightly dropping. And this is another question to think about, why it's dropping. So the Oracle one is actually like as we expect. So we argued that this GLS, or the Oracle GLS, you want to call it, is basically equivalent to the OLS in transform domain, and we proved that, I mean, you could use the kind of the T distribution to set the basic threshold for these confidence intervals as kind of exact, like near exact, as far as finite sample can go. But you lose calibration in this feasible GLS, and it's worth thinking about. Why? What is the difference between the two? Okay, so this plot is very interesting, I would say. And you can also see that if you have serial correlation, if you use OLS, your confidence intervals would be too optimistic, too narrow. Okay, so you underestimate the noise variance. Sorry, the variance in your estimates, or the variance, yeah. Questions? I want to basically wrap up here, so I'm not going to discuss too much this further. Maybe just one more comment about that. But you have any questions about the feasible GLS? So the last piece is this MMRM, which is also very popular in clinical trials, mixed models for repeated measures. The exact form is not really that important. The idea is that we have patients that are measured. Let's say you have patient I that comes in at different times. I is the index of the patient, T is the time that they come in. Like, let's say there's a time 0, which is the baseline. They come in, like you get the measurements, and then you give them the treatment, and then they come in, let's say, in 2 weeks, and then 4 weeks, and 6 weeks. This is the other side. So T, for example, could go from 1 to 3, let's say 4, something like that. And then I goes from 1 to N. So these are patients. So for each patient, you see or you observe a sequence of these measurements. And the idea is that these measurements for each patient, they're going to be correlated because they're across time for the same patient. For different patients, they could be uncorrelated, but for the same patient, they're correlated. And so you write down this model that, so there's a baseline covariate and there's the treatment. This is like 0, 1. It indicates like whether they receive the treatment or not. And then you have these coefficients here that could depend on time. And then there's the noise, which is, and then the intercept also could depend on time. And there's the noise, which depends on both the person, the patient, and time. And so these noises can be correlated, okay, across time. And so you're back in the same situation that we were let's say in the previous example. And you can write this down properly in the matrix format. I mean, I'll let you look at this for yourself. And the matrix format will be something like this. So you end up for every patient, you can capture all the observations into yi. So you have m observations, and then you would have a design matrix which depends on patient I, and then times beta epsilon. And then the issue is that these covariance matrices are not going to be, the covariance of epsilon i's are going to be per patient covariances, and they're not going to be um, um, like sigma i's are not going to be a scale multiple identity. Okay, so the noise for different patients will be uncorrelated or independent, depending how you want to handle it. But the fact that this is not identity or a scale multiple identity is the problem. Okay, so once you put everything together, you get like a giant noise vector, which we can call it omega, let's say, and we block diagonal with these diagonal covariances, and so these are unknown. Yes.
I know that omega stands for like the block diagonal matrix, or but why is sigma not used in these cases? I remember like sigma was used for the covariance matrix before.
We should use sigma. It's possible. I mean, I don't know why there's omega. It doesn't matter. No, omega is usually used for the precision, but this notation is not a standard. It's just, don't worry about the notation here, right? It doesn't matter what you call it. It's just a block diagonal matrix, right? No, this is minor, so ignore this. This is not yeah. Omega is actually usually used for precision. Why we call it that, I don't remember. But it may not be a standard. You can call it sigma if you want. And the the idea is that these are unknown, and then you can impose different constraints. So you could do feasible GLS. GLS would look like this, but this omega or sigma is not known. And then you can try to impose a structure on these covariance matrices, and then you can try to estimate them jointly with everything else, like by maximum likelihood or by restricted maximum likelihood. We're not going to go into that. But in the end, so you have an estimate, you plug it in, and you get this kind of something like a feasible GLS, and then you can use like the machinery that we have. Okay, I just want to point it out. This is not something that I want to spend too much time on. If you don't have any questions, let's move on, because we want to actually talk about what material in lecture 14, which is today's lecture. Questions? Okay, so that was just basically wrapping up the previous discussion about the blue Gauss-Markov idea. So what I want to talk today is going back to what happens. So remember, this covariance matrix of beta hat is sigma squared x transpose x inverse. So what happens if x is fails or nearly fails that full rank assumption? If you recall, we had the assumption that x is full rank, and what that does is, anyone remembers what the assumption did for us, like the x being full rank? So we made the assumption that x, yes. Yes, okay, so it tells you that x transpose x is also full rank, which means it is invertible. So at least I can write, and this makes sense. But what other consequences did it have, like from a statistical perspective? Yes. Unique beta, yes. So we could, like, it would make beta identifiable, actually. Exactly. So that's the key property. If you recall, so x beta would be identifiable always, but beta may not be. So if I have mu, I may not be able to find a unique beta if the columns are linearly dependent, columns of x, and that would have a huge impact because we're trying to estimate beta, but I can't actually identify which beta. So today we're going to talk about like failure of the assumption, uh, not exact failure, but approximate failure. Okay, so you could still have full rank. Full rank is like a binary property. It's either full rank or not, but it can be close to not being full rank. Okay, so if the columns are nearly linearly independent, we want to see what happens, and this can be characterized via the eigenvalues. One way to characterize the this near failure is via the eigenvalues. This X transpose X will have very small eigenvalues. And then, for example, X transpose X inverse will have huge eigenvalues. And because this is related to the variances of beta, the betas would have the beta hat would have big variances. So near failure of it is reflected uh, on the statistics side as large variances of beta hat. But we want to understand this phenomena a little bit more in more depth, let's say, okay, more deeply. So what happens, we'll see, is that there are some linear combination of the coefficients that will have large variances in general. And then, although OLS has the smallest variance, it could be like the best of a bad lot. Okay, so let's say all unbiased estimators could be bad in the sense that they produce large variances. So this is the minimum variance, but still the variances would be large. So the way that we're going to do it is, let's say, there are two viewpoints. One is more, I would say, modern or spectral via the eigenvalue decomposition and the spectral properties of this. The other one is a little more classical and it's interesting as well, which is the root via like the variance inflation factor, VIF, that we're going to discuss. And then we'll discuss briefly like a fix, a modern fix, if like via the ridge regression idea. So that's basically the plan. So before doing that, there's this aside here that it might be a little bit cryptic, but what I'm going to work with mostly is like a centered version of the X, the design matrix. So if the actual design was like this matrix, matrix of one, like you have columns of all ones, and these are the columns corresponding to the predictors, I can uh, basically project all the columns onto the columns of all ones and take the residual. So I remove, so let's say this is, if you remember, or have we discussed something like this. So anyone remembers what this matrix is? I minus 1, 1 transpose divided by n. It's a projection matrix. And it projects onto the orthogonal complement of the span of all ones. If you remember, we did the F test when we set all the covariance equal to 0 except the intercept. This would be the operator that produces the residual. So this effectively applied to a vector, it centers the vector. Okay, so takes the average of the entries and removes it. Okay, so what we're going to do is that we're going to apply this matrix M1 to every columns of Z, and this would center all the coordinates. And then you could show that let's say if beta corresponds to this part in our case, let's say, I don't want to look at the intercept. I want to look at only the coefficients corresponding to the real predictors. You can show that the covariance of beta hat would then be, again, something like this, sigma squared X transpose X, where X is now the mean version or the centered version. This is not at all obvious, but at some point in the course, hopefully it becomes clear why, I mean, they look similar, but here, let's say, originally, for example, you had like beta 0 up to beta p. This is how we dealt with this. Now I want to call this part beta. And if I call this part beta, the covariance of that part is not going to be, it's going to be the corresponding block of this, but it's not going to be an easy, as easy as this. But this X here is not the same X. It's like modified X after I do the centering. Yeah, and I don't want to dwell too much on this, but just have this notation. At some point later in the course, this becomes a little more clear. Okay, or you can think of let's say the intercept, we don't have any intercept, and all the columns are centered. If you think of it, this would be the same as this. But because we don't have too much time, I don't want to spend too much time. Either way, it's easier to center all the columns for the discussion, and then don't worry about the intercept. Anyway, so let's start. What I want to do is consider this model. Yi is 1 plus 2xi plus 3xi2. This is like a regression problem with two covariates. This is like our beta 1, this is our beta 2. Let me call this gamma 0 because I'm calling these two beta. I'm ignoring the intercept. So what happens here is that the noise is like standard normal, like satisfies our best of assumptions, n is 50. And then the correlation, let's say the sample correlation between x1 and x2, the two columns, is 0.999. Okay, highly correlated columns. And then that's this case. So I look at the beta hat 1 and beta hat 2. These are the OLS, and for each experiment, I'm going to repeat the experiment 500 times. For each experiment, I get a point. Okay, and then I plot these points. So this is going to be a point cloud of the two. This is the case where the correlation between the two covariates or the predictors is 0.99. This is the case where the correlation is 0. Okay, and so you can see the different, they look very different. In this case, they're kind of, the variance is kind of low, and they're basically gathered around the origin. Here, they're going to spread out hugely. And nothing has changed here except the correlation between the predictors. Okay. So this is the phenomena. This is called like the issue that we were going to discuss, which is called multicollinearity. So I have two vectors here that are nearly in the same direction. So correlation here, let's say if you think of them as being centered, which we roughly centered them, this correlation is close to taking the inner product, if you standardize the inner product. And so they're saying they're in the same direction. So what you notice is that they are spread out along a particular line, and that line is beta hat 1 plus beta hat 2 is equal to 5. And this is no coincidence. So what this is saying is the 5 is just this 2 plus 3. So because these are nearly along the same line, in the ideal case when the correlation is exactly 1, basically x1 would be equal to x2. So I can write y is equal to 1 plus 2x1 roughly plus 3x1 plus epsilon. So then I can just sum them, like I get 5 times x1. So you get y is equal to 1 plus 5x1 plus epsilon. That's approximately true. And then equivalent, effectively, you're estimating this 5. So the sum of the individual coefficients are not identifiable, but their sum is identifiable. Okay. In other words, I have a lot of information about the sum because if I look at any one of them, I can like the sum is kind of constant along the line. The sum is 5, but in the other direction, I can't tell you anything. Like we'll see, like beta hat 1 minus beta hat 2. Basically, we don't have any information about the difference. The difference would be like lying along this line. Okay, so along this line, there's no spread. So there's like, this tells you exactly, so this would be, for example, beta hat 1 plus beta hat 2 is equal to 6. Nothing there, okay? It's highly concentrated around this, but in this other orthogonal direction, it's just completely wide. So it's like anywhere from this to this. So beta hat 1 could be beta hat, this is like the direction of beta hat 1 minus beta hat 2. It's highly variable in this direction. It has very low variance in this direction. So we can determine this very precisely. So this is a good estimate of beta 1 plus beta 2. I can estimate beta 1 plus beta 2 perfectly, but this is an estimate of beta 1 minus beta 2. I have kind of very bad information, highly variable estimate of this. Okay, this aligns with the fact that individual betas are nearly identifiable, but the sum is identifiable here. Okay, and that particular direction you can identify using the eigendecomposition. There are certain directions that are more informative. You can estimate the parameters in those directions more informatively than other directions. And this happens as you approach multicollinearity. Is this kind of clear? This picture kind of explains the whole thing. We're going to just maybe explore using various tools like this phenomena. Questions? Yes.
Do you have added just the covariance between two things to make like one like the graph? Are there visualizations where you take the covariance of like each of the variables without one variable and like they should repeat like
So this is not a covariance plot. There's no covariance. There's also not direct. I'm not plotting I'm just plotting this point, beta hat 1, beta hat 2, right? The covariance like implicitly comes in. The covariance of x1 and x2 implicitly comes in. We'll see. I mean, so let me, because we don't have much time, I spent too much time on the first half. Let me go through, and then if you have questions, let's see if they're answered in the subsequent slides. So the exact multicollinearity is when the rank is less than, let's say we have just P. Remember, we have P now. X has P columns after removing the effect of the intercept. So if the rank is less than P, you have exact multicollinearity. Some of the columns can be written as linear combination. The other ones, then X transpose X is singular, beta hat is not unique, or beta is not identifiable. Not identifiable. The alternative is there is no multicollinearity, but you can approximately be close to multicollinearity, and that's the case where you have some sort of like a unit vector such that xv is nearly zero. Okay, if xv is exactly zero, that sort of violates the linear independence. But if it's nearly zero, that's like numerically close, and so it means like this norm of xv squared is close to zero, and that direction is not identifiable. We'll see. If you, for example, try to do v transpose beta for that v, this you'll have problem. This is nearly identifiable. So some of the things to remember that is the mu hat is always going to be stable. So there's going to be a unique projection no matter what. This is the issue of the basis. So the coordinates are not stable because you can rewrite beta hat in different ways as linear combination of the columns. So that's kind of the issue. And this V is going to be, yeah, so let's call this contrast if you want. These new parameters, V transpose beta. For the V that does this, we can't really estimate this. So these parameters would be unidentifiable. So to see this, let's do the eigendecomposition. So X transpose X is symmetric, remember? And we have eigendecomposition. X transpose X is like V lambda V transpose lambda. So this is like the columns of V are the eigenvectors. Columns are eigenvectors. And then the elements on the diagonal of lambda are the eigenvalues. Eigenvalues. An equivalent way of rewriting this is in this form. So if you, so V has these columns, V1 up to Vp. Okay, and lambda is like lambda 1 up to lambda p. If you expand, you can have this expansion, which we discussed early on, is a very nice interpretation of the action of the operator. So the first one, basically, if you multiply by a vector, let's say if you multiply this by a, you can see what happens. If I multiply by a, this takes, basically projects a along the eigenvectors. So these are the coefficients in the new basis, and you scale those coefficients by the eigenvalue and then put them back in the direction of vk. And so you scale different coefficients of, like the coefficients of a vector in the basis specified by the eigenvectors exactly by, you scale them by the eigenvalues and then put them back along the same directions and you put back the vector. So that's how this operates. And if you do this, then it's very easy to argue, especially from this point, like X transpose X inverse would be V lambda inverse V transpose. This you can easily check by multiplying this expression and this expression, and then argue that it would be identity. Okay, so you just have to invert the middle diagonal matrix when you invert an eigen decomposition kind of expansion. And so this is equivalent to writing it like this. So when I invert it, it's equivalently written in this way. So the eigenvectors of this matrix are the same. The eigenvalues are the inverse of the eigenvalues of the original matrix. So why this is useful? Because now if I look at the contrast, let's call this A transpose beta. If I want to predict or estimate it, we have this plug-in estimator, A transpose beta hat. We knew, or we had calculated the variance of A transpose beta hat. If you recall, most of you hopefully recall, there's A transpose covariance of beta hat A. This is going to be sigma squared X transpose X inverse. So you get sigma squared A transpose X inverse A. And then I plug in, let's say if I look at this part, you get A transpose summation K, lambda K, VK transpose A. And then I pull A inside, A transpose goes inside. I get this expression. Okay, I can move the A transpose and A inside. And then I notice that the claim that these two quantities are equal. A transpose VK and VK transpose A are the same. Why is that? So they're transposes of each other. They claim that they're the same actually quantity. So for example, I can write it as summation lambda K A transpose VK is squared. I keep one of them squared. So why these two are the same? Anyone? So this quantity is a scalar, okay? And one of them is the transpose of the other. So if you transpose A transpose VK, you get VK transpose A. Because they're a scalar, the scalar is equal to its transpose. Okay, the scalar quantity, if you transpose it itself, so they have to be the same thing. This is very useful if you do these matrix calculation, because I can just use one and a square it. And this is exactly what we did here. Actually, there should be lambda inverse, right? And if you do it, you'd get this expression. Okay, so you have this nice expression, sigma squared, and then you have this expression of the variance of this in terms of, so you basically look at the coefficients of A in the basis, you square them and then scale them by the inverse of the variance, like the eigenvalues. Why this is interesting, because let's say if you look at, here I'm organizing or ordering the eigenvalues as in this way. So lambda 1 is the largest, lambda p is the smallest. So v1 is the eigenvector corresponding to the largest eigenvalue. Vp is the eigenvectors corresponding, or eigenvector corresponding to the smallest eigenvalue. If I take A in that formula to be Vp, which is the smallest eigenvector corresponding to the smallest eigenvalue, so these eigenvectors are orthogonal to each other. Okay, so every element here would be 0 except when k is equal to p. In this case, I get Vp transpose Vp, which is going to be 1, because they're unit norm. Right, so I get just 1 over lambda p here. Okay, and if I look at the V1, which is the, basically if you do it for any Vk, the general idea is that the variance of Vk transpose beta hat would be sigma squared over lambda k. If you look at the direction Vk, because all these eigenvectors are orthogonal and they have unit norm, only one of the terms in the sum would be non-zero. Okay, and so the variance would, you can see it's like rescaled by the inverse of the eigenvalue. So the one that it has the smallest eigenvalue would have the largest variance. The one that has the largest eigenvalue would have the smallest variance. So this, for example, in the example that I did in the picture, this V1 would be corresponding to what? To vector 1, 1. That's the direction that I get, like the variance of beta hat 1 plus beta hat 2. This is very small. This direction, if you do the basically eigen decomposition, this would be 1 minus 1. So this would be beta hat 1 minus beta hat 2 corresponds to the small eigenvalues, so the variance of that would be very large. So you have these two directions. This direction corresponds to V1, this direction corresponds to VP. Okay, and they're orthogonal. You can see the directions are orthogonal because these eigenvectors are orthogonal. Does this kind of make sense? And as one of the eigenvalues approaches 0, so when you approach multicollinearity, the smallest eigenvalue approaches 0. So this one is going to blow up. And maybe a couple more. It could be like you have a sequence of very small eigenvalues. All these directions would be unidentifiable, nearly unidentifiable. So those estimates, you can't, for example, tell me the difference between the beta 1 and beta 2 accurately, but you can tell me the sum accurately. Okay. That's the kind of the gist of. Does it make sense? So do this for the basically, if you do the like frame 2 example, it's like would be like something like 1.99. If you do the eigen decomposition, the top eigenvalue would correspond to this eigenvector. So it would be something like 1 over root 2, 1, 1. Say 1 over root 2 because we have to normalize them. And then you get something which is, sorry. Yeah, it would be V would be like 1 over root 2, 1, 1, 1 minus 1. And then this would be something very large and then something very small. And then the transpose of this. Okay. And so this direction is exactly the direction of the largest eigenvalue. This is the direction of the smallest. And it corresponds to which linear combination of beta you can accurately estimate and which one you can't. You don't look very happy. So, any questions? It's a very nice, like, geometric picture. Okay, so there are these directions. Maybe I'll keep a little bit going because so there are these directions that are kind of measure the relation of the predictors together. So in fact, if you imagine the xi's are IID, this is like the random design perspective. For most of the course, we think of the x's as fixed. But if you imagine in practice, they're generated from a distribution. And so these are now the rows. Yeah, it should be like, if you have the x, these are the rows. Xi transpose is the ith row. You can think of them as coming from a distribution, like their IID, let's say, from a p-dimensional distribution with covariance matrix sigma x. Then you can argue that this is going to be an estimate of the covariance matrix. This is actually by the law of large number. You have done it in your homework problems. This would be xi transpose, something like that, I believe. And so this converges by the law of large numbers to the expectation of one of them. Here we are assuming that there's zero mean, so this is going to be the covariance matrix. So this is the law of large numbers. Okay, so this converges to covariance matrix, and so you can rewrite this covariance of beta hat is really another way of writing it. I can divide and multiply by n. And so this is going to approach the sigma x inverse. Okay, sigma x captures like the relation between the predictors. It's the covariance matrix of the predictors. And so this is the scale, the natural scaling. This is the natural noise level of the problem. So if you have imagine if you have like a sample average and the noise in each one is sigma squared, the average would have sigma squared over n variance. So this is the typical variance that you'd expect for the noise level sigma squared. If you if you average over n samples, this appears here, but then there is a curve, like a part which stabilizes in the limit, which is the sigma x inverse. And this is exactly like the same thing that we discussed, it's just that I normalized this by n. And now if you do the eigen decomposition here, I mean, the same idea. The only difference now is that these are going to be scaled by n. You can rewrite this as the same thing. So sigma squared over n, 1 over lk mu k, and then you get covariance of A transpose beta hat is sigma squared over n. Summation lk A transpose uk. If you have seen PCA, principal component analysis? So this is exactly PCA done on the x vectors. Okay, so if you look at the scaled version, this is really approximately the covariance matrix of the predictors, and I'm doing the eigen decomposition, and then basically the covariance A transpose beta hat would have exactly the same formula, except now I'm putting n here and then basically dividing this by n as well. So this would be lk. So you can view it as basically the PCA of x is informing you about these directions. Okay. That might be a little bit too much, but there's nothing new. I just wanted to point out that this is really PCA. Okay, so you do PCA on x, and maybe this could be VK. I mean, the reason why they're UK because they're at the population level. It's like approximately, this is approximately VK, and this is approximately lambda k divided by n. Okay. Okay, so the directions along the kth principal component of the x are inflated by this amount. Yes.
The highest variance explained by that.
So yeah, so what these mean is like the direction corresponding to the largest eigenvalue is the direction of not explained, but is the direction of the highest spread in the data. So if you have a two-dimensional, it would be a little confusing with the data, but it's just you would how should I say it so that it's not getting confused? It's the exact same picture here. So for example, if you have a covariance matrix, if this was the actual x's, if you plot x like you have bivariate x and you plot them the point cloud, and if the covariance is nearly rank deficient, you would observe this picture. So the direction this direction that points in the direction of the maximal spread is corresponding to the largest eigenvalue. This corresponds to the smallest eigenvalue. The problem is that in this picture, the thing is reversed because this is going to be really confusing, but it's very interesting. So if you look at covariance of beta, it's just a sigma x inverse rather than sigma x. So if you look at the point cloud of x, let's say in R2, let's say two-dimensional, the direction that is maximally, you have maximal variance along is the direction of the largest eigenvalue. If you look at the betas, because they're just the inverse of the sigma x, the direction that you have the maximal spread is the direction of the smallest eigenvalue. But it's the same picture, okay? So this is because the covariance of beta hat is just the inverse of, so you can think of this as, we are doing PCA of beta hat if you want. But it's kind of related to the PCA of x. Does that make sense or too confusing? So the idea is that you have a covariance matrix that the eigenvectors explain the direction of the spread. Okay, in the traditional PCA, because you're looking at the sigma x itself, so this explains the variance. So for example, variance of A transpose X as a vector would be A transpose sigma XA. And so if you write down the formula, you'd get, this would be summation LK UK transpose A squared. So the direction that corresponds to the largest eigenvalue would have the highest variance. In contrast here, well, we're inverting that covariance matrix, so this is going to appear in the denominator. So the direction corresponding to the smallest eigenvalue would have the highest spread, okay, because we're looking at the inverse of the covariance matrix. Did not help, okay. The general picture is interesting, but the covariance of beta is basically the inverse of the covariance of x. So in the direction in which, if you look at the exospace, the direction of they are maximally spread out is the best for beta. Okay, beta in that direction would be having less variance. The directions that they have less variance in is maximally worse for beta. If you think about it, it makes a lot of sense. So if x's vary a lot in a certain direction, you can tell beta in that direction well. But if x's vary little in a direction, they're like highly correlated in that. And in that direction, they're not varying, so they're tight together. And so in that direction, you can't tell beta apart. So the relation is kind of inverse. So you just have to think about it a little bit. It's not obvious, but like the math tells you this. So the reason why this happens, exactly the same decomposition happens. So this matrix, the two matrices have the exact same. So the covariance, like if you ignore this prefactor, the covariance of um, beta hat is exactly the same as the covariance of x, but inverse. And so the eigenvectors, the directions are the same. It's just that the eigenvalues are reversed. And so what is large there is small here. And so they kind of behave oppositely. The direction in which you're maximally spread in the x direction is the direction you're minimally spread in the beta hat. So that's good. The direction in that you're minimally spread in the x direction, that's where you maximally spread in beta hat, which is bad. Okay, that's the best I can do for now. So questions? This is a very nice geometric idea. The other idea is the traditional idea, which I'm just going to briefly mention. So if you have, if you just care about, let's say, the variance of beta hat, people have noticed traditionally that you could do a very nice decomposition. If I look at the variance of beta hat, I can write it in this fashion. So there's this, this is really another way of writing. So this is like sigma squared x transpose x inverse, the jth direction. Sorry, the jth coordinate, there's no direction here. Jth coordinate, I can write it in this nice form. There is this part which is sigma squared roughly divided by n. That's the part that we already see. There's the variance, sample variance of the jth column, which is like individual predictors. And then there is this factor which is related to the interaction of the predictors. So what is this factor? Is 1 minus rj squared. And this rj squared is the r squared, the coefficient of determination, in a particular regression. So if I try, so the idea is that I'm going to try to predict xj based on all the other predictors. I'm going to regress xj onto the other predictors, and or let's say, okay, onto the intercept, and we already did it on the intercept. So I'm going to regress the xj onto the other predictors, and this gives me a regression problem, and it gives me an r squared, which tells me how well this works, okay? Let's call the r squared in that problem j squared, and let's call the residual in that problem xj. So this is the residual after I project basically xj onto the other predictors and basically take the residual. The idea is that the variance of beta hat j can be written as sigma squared divided by the norm of that residual. which happens to be of this form, and where this is Rj, and from this formula comes. So I'm not going to discuss the proof. Maybe at some point again, this FWL idea is related to these residualization. If we see it, the proof of this becomes a little bit more clear. The main point is this idea that I can try to measure how correlated things are by trying to regress one onto others. If I regress xj onto the other predictors, and r squared is very close to 1, it means that like xj is nearly a linear combination of the other ones. So we're nearly multicollinear. And so this rj would be close to 1, and you can see 1 minus rj would be close to 0, and this blows up. Okay, so this naturally tells you that if rj squared is 0, it means that when I try to project xj onto the other ones, I try to predict based on the other ones, I have a bad regression. I can't predict, so the rj squared, remember, it's like a measure of how well you can predict. So xj has really new information. It cannot be predicted by the linear combination of the other one. This is 0, and this factor will be 1. Okay, so this naturally captures how much of the variance of beta hat j is inflated because of the intercorrelation of the J predictor with the other ones. If the J predictor can be explained by the other ones, this is not very identifiable. Okay, and this is another picture if you just care about the individual beta hat J's. And this idea of like trying to regress one predictor onto the others is very useful. Okay, we'll maybe see it later. You can work with the residual of that, and ideally, for example, you can only include the residual, because the residual is the new part. The part that you project can already be explained by the other predictors. But that's called the VIF, variance inflation factor for the Jade beta. And this multiplicative factor is basically like summarizes all the information, like how the dependence like affects the variance of beta hat j. And then there's, if you look at the C, which is the sample covariance, sample correlation of the columns, there's another formula for this. Your book uses C inverse JJ. So if you form the sample correlation matrix, these are the real predictors, not the intercept. And then invert it and look at the J coordinate, that will be exactly this quantity. These are all things that you can show. Let me show you an example here. This is from your book. So you have this regression, you're trying to predict, let's say this is the sale, the sales in dollars of like a pizza joint. And then you're trying to predict this based on two covariates, which are the number of ads and the cost of the ads that they ran. And the number of ads and the cost of the ads are usually very correlated. If each ad costs the same, then the cost would be the number times that fixed value. But if they're slightly variable in price, still they're highly correlated. They're not going to be exactly collinear, but they're close. And in this case, there's data in the book. You can compute the C matrix. You can see like the sample correlation between the two is high, 0.885. You invert it, you get this value here. And the VIF of both would be 3.6, which means that the variance is inflated by about 3.6 relative to the case where you have zero correlation. And then there's also the condition number of the matrix, which is high, like 12. And so other ways you can see that this issue, there's this multicollinearity present here, is if I, for example, drop one of these and refit the model, the R squared doesn't change much. So if I do both, if I include both, R squared is 0.77. If I include only x1, it's 0.73. If I only include x2, it's 0.75. So you can see if I drop the covariates, they're not as informative for the overall fit. The other way that you can see it is if I do a joint test, of setting both of them equal to 0. If I do an F test, try to test the null hypothesis that beta 1 is equal to beta 2 is equal to 0, that would be rejected in this case because the fit is good, 77. But if I individually test whether I can drop, let's say, beta 1 in the presence of beta 2, that's a t-test, that would generally not be rejected. If I test beta 1 equal to 0 individually, it wouldn't be rejected. If I test beta 2, can I drop this to 0? It would be not rejected. It means that I can set it equal to 0. Okay, so I can set equal to 0 individual ones, but I can't set both to 0. So this behavior suggests that they're highly collinear. Okay, I can drop one, nothing changes. So that's the t-test. If I drop both, I lose a lot. So this is saying they're predictive, but I don't need both. Just maybe just one last slide, just very briefly. The modern way to deal with this multicollinearity, one way is to remove some of the predictors that are collinear. That's the traditional way if you care about the betas. But another way of doing it, which is much more modern, is to shrink. So what you're going to do is you add a penalty. You add a penalty to the least of squares, like lambda beta squared the norm of beta. And this would add, you can show that this would add this lambda I here. And when you go and do the eigen decomposition, the only effect is that it would just add lambda to all these eigenvalues. Adding lambda I to a matrix is just add the eigenvalues. Just the same constant shifts all the eigenvalues. And when I invert it, I have this extra lambda in the denominator. So even if lambda k approaches 0, this lambda here prevents this from blowing up. So this allows me to trade off. I have a knob now, like lambda, that I can like vary and allows me to trade off bias for the variance. So if this lambda is very large, the variance drops, but the bias increases. So we're going to leave the land of unbiasedness. So this estimator will be biased, but this extra bias, a little bit of it allows me to reduce the variance a lot. So we'll hopefully see this like so-called bias variance trade-off of ridge regression. This is called ridge regression later in the course. Okay, that's it. Thank you. And see you next time.